Hello everybody, welcome to Thermodynamics Lecture 22. I'm here on Sunday giving you this lecture to talk a little bit about thermodynamics heat integration with the first law in Chapter 4. So we are almost finished with Chapter 4 and we'll be moving on to transient analysis for Wednesday's lecture, and then I may have a special laboratory lecture that I'm going to put together by the end of the week, which may be an extra bonus since we've lost a day last week with a day off on Monday. So we may add an extra video lecture that will be a lab assignment for you guys. Even though I was really hoping to have the lab assignment in class like we did with the syringes, which was super fun. But looks like we're not going to be able to do that here. So I'll do that experiment for you, and then hopefully we can do some homework assignment with that over the weekend. So stay tuned for that. So other news. So we are still working on the surveys. The surveys are going pretty well. I made a little bit of a mess up on the survey, and that there were 2 survey 17s in the grade book. So some people got grades for survey 17, even though they were the previous survey 17, so it got a little bit messed up. I'm sorry about that. I changed that, and I just gave everybody 1s for it because most of you participated. And I want to take a look right now at the results. So let's do that right now and take a look and see what that looks like. So if we go here, yeah. So this was the answer. So every day I'm going to go through the answer to the previous survey, because that way we can learn something from our mistakes. Looks like people did pretty well today, so that's pretty awesome. So what is true about the exit state of an adiabatic throttling valve that has gas flowing through it? Well, adiabatic, right? And it's a throttling valve, so we know the pressure is decreased because of the throttling valve. And we know the velocity has to go up because it's a throttling valve, so the pressure goes down, the velocity goes up. Okay, it's not a supersonic diffuser or anything like that, so none of that funny stuff. So most of you got it right. If you see here, I had 56 total responses, which isn't bad considering, the craziness of last week. We had a few people still kind of on the fringes here. So the idea is that as I said, in an adiabatic throttling valve, which means there's no heat transfer, the pressure is lower than the inlet and the velocity is higher than the inlet, right? So the velocity is higher as it goes through. And we did that when we did that example problem in the last video lecture. I showed that example problem of that junk that was inside the tube, which was causing the velocity to go up by a lot, and the pressure drops considerably going through that restriction. I don't know if you remember that. Hopefully you do. If not, you can always go back. It's on YouTube. Okay, got to keep the coffee coming in. All right, so let's move on here. So that's pretty much all the announcements I have. I think everybody's doing a really great job with the lectures. I'm getting some pretty good feedback with the YouTube link. I'm pretty sure that this is a much better way to go. So we're gonna stick on with the YouTube and keep going that way. Anything else? No, homework's just as usual. Hopefully I haven't gotten any questions about the homework, so I'm assuming you guys are able to do those, no problem, okay? The TAs are still behind in the homework grading, but that was the same before we went online, and it's the same now. So I'll keep pressuring them to get those homework assignments back to you. Okay, let's move on here. So let me go to the lecture slides for today. Now, today I want to talk a little bit about what we call system integration. So this is still steady state, right? Meaning that the systems are completely going steady. There's no change in the control volume. There's no change inside of each of the control volumes. But in this case, engineers can combine components to achieve some overall objectives subject to constraints, such as minimal cost, blah, blah, blah. Or you're putting together a cycle. This is another reason why you might have system integration, right? You have a cycle. In this case, this activity is called system integration, right? So we're putting together a system that minimizes something, or you have a system that encompasses a bunch of different steady state devices, including nozzles and pumps and turbines and all these other things all together. We call that a system. The beautiful thing about doing control volume analysis is that you can just draw control volume around the whole thing, or you can draw control volumes around individual pieces of the whole thing, which we're going to demonstrate a little bit today. okay, in the example problems. I have a pretty lengthy example problem and then kind of a more interesting example problem. And that's all we're going to do today is just kind of cover these things. We've covered all these components. For example, this is a simple power plant. When we talk about power plants later when we do cycle analysis, which hopefully will come after we talk about second law, we talk about a system that looks like this. So this is what you would have in a vapor power plant. Vapor power plant is otherwise known as like a steam power plant, for example, where you might burn coal that puts some power into the boiler, which is Q in right here, and then you make a whole bunch of steam and you send that through a turbine, and then that steam comes out of the turbine at some subcooled, or maybe it's not subcooled, maybe it's just saturated steam, comes out and condenses, goes back across the vapor dome. You lose some heat. Usually this condenser is done with some river water or a cooling tower or something like that. And then you go through a pump, and then you pump that water back through again, okay? And then you've got a system, okay? It's a simple vapor power cycle. Vapor refrigeration cycle is the opposite of this, goes the other direction, which we will learn. And then you put some work into the pump, you get some work out of the turbine, Q in, Q out, okay? Straightforward stuff. I think you could put a whole box around this thing and not worry a single whit about what's happening inside here in these individual components. Once you put a control volume around the outside, all you're worried about is what's crossing the boundary, right? So for example, you have Q in, you have Q out, you have work of the pump, work of the turbine. Those are the only things that are crossing the boundary, so you don't have to you don't have to worry about all the different streams. However, if we were to ask you what's the state at the end of the boiler, at the exit of the boiler rather, you would need to know something about the inlet to the boiler, and then you'd probably have to take your box around the boiler itself. Okay, your control volume would have to be around the boiler itself in that case. So it's just a matter of what you're being asked in the problem, okay? And that determines where you take your control volume boundary for different parts of the problem. Okay? So let's see what we can do with some example problems, and then I'm gonna wrap up with maybe some. Well, if I can do a little bit of transient, I will, but I'll see if we can get through these example problems first. Okay, oops, what happened to myself? I disappeared. All right, there we go, that's what I want to do. Okay, so system integration example. So separate streams of air and water flow through a compressor. So there's actually, if you just look at it here, we've got two compressors, okay? Let me log into my, let me log onto my tablet here so I can, don't block me out of my tablet. Okay, okay, yeah, so we have two different compressors as you see in this diagram, right? You've got, oops, I'm covering up some of this, so I just put myself down here. That's better. Okay, you got two different systems here. You've got two different compressors and a heat exchanger. These are things we've both gone over. So a compressor is taking air, in this case, at 1 bar, atmospheric pressure and atmospheric temperature and some flow rate, and compressing it to 3 bars, 600 K. And then you're going through here, you're going to compress it again, right? So your ultimate goal is to make 9 bar air and a temperature of 800. You're going to put work into each of these control volumes, or compressor A's and compressor B's. Here the beautiful thing is that you've got a heat exchanger, and what you'll find when we do second law analysis of these types of things is this cooling in between heat exchangers is really, or in between compressors, is really advantageous because it allows the compressor to be more efficient. So this is called intercooling. Sometimes in really fancy cars where they have big engines that have different stages of turbocharging. I don't know if you know anything about turbocharging. If you're a motorhead like me, you know what turbocharging is. Essentially, you're compressing the air before you put it into the engine, okay? And in this case, if you had a two-stage compressor like this, where you had one compressor and then a cooler and then another compressor, you can get really high pressures while still maintaining low temperatures, which is something you want. 800 K is not that low, but okay. So anyways, on the other side, we've got a heat exchanger with water going through it. So your water going through the heat exchanger that's cooling this. And this water comes in at 20 C and goes out at 30 C. Maybe there's a radiator over here dumping that heat somewhere. Who knows? I don't know. But that's not our concern. So what's our concern? So what we're talking about here is let me just switch to the this. Okay, so it's the same. I just put it on my tablet so we can solve this problem. So yeah, so we have separate streams of air and water flow through the compressor and heat exchanger arrangement shown in the figure, steady state operating data. So this is kind of key stuff, right? When they say steady state, we're saying, that's something to pick out. Operating data are provided in the figure. Heat transfer with the surroundings can be neglected. So this is neglect heat transfer. That's another key thing to pick out, right? So we always pick that out. It means adiabatic, right? As can all kinetic and potential energy effects. So that means we can neglect potential and kinetic energy effects, which is also cool. And the air is modeled as an ideal gas. So these are all key assumptions that we can make in this problem. Notice that it doesn't say use constant specific heats, okay? If it said use constant specific heats, then you can. But otherwise, no, don't do it, okay? So total power required by both compressors is what we need to find, and the mass flow rate of the water in kilograms. Okay, so kilograms per second. Okay, so let's see here. Let's see. So we're gonna just start our problem here. Let's see if I can view this as a page. Oops, no, that's not. I don't want to have fancy. I don't want to have fancy single page. That's what I want. Okay. All right. So what I do is as page. I like doing things in page wise. So okay, known. So known is that we've got a two compressors with intercool. I'm going to call it an intercooler. Oops. Two compressors with an intercooler, air and water system. Okay, what we have to find, we need to find C, what do they call it? I think they call it CA, and work.CB. Notice it says it wants it in kilowatts, right? So it wants it in kilowatts. That means that it's big W dot, right? Big W dot is kilojoules per second, or otherwise known as kilowatts, okay? So just beware, that's what they want. And B, we want to find mass flow of the water. So water in kilograms per second. Okay, that's how much water is going through in order to cool the stream. All right, so what this requires is that we're going to take different control volumes, okay? So we can't just take the whole system because we're being asked what's happening into these individual different states. So what we're going to do is we're going to make some assumptions first. Okay, so some assumptions we're going to make. One we're going to make is air is an ideal gas. Okay, two, we're going to say that we're going to say it's steady state. Both are steady state. Three, we're going to say it's adiabatic. And no delta KE or PE. Well, isn't that convenient? Okay, and I think that's what we got, right? So I don't think we have anything else. Did we say it's steady state? It's air is modeled to gas. So we're going to also assume that the water is incompressible. That just means that essentially we're going to assume that V of the water is equal to VF from the steam tables, right? And H is equal to HF at the steam tables. All right, so that's just what we're going to say. So there's no dependence on pressure, just temperature. At some temperature. Okay? All right, good. So we're good to go here. Now I think we know what we're going to do. We have to find out what these different things are. So let's just continue on and do it. So in the analysis, well, let's make some diagrams first. So let's make some diagrams. The first thing we're going to do here is we're going to say that we're going to put in, well, here, I guess I'm going to have room here. So we're going to have one compressor here. We're going to have two compressors here. You've got, oops, erased it. Okay, so you have work compressor A. You have work of compressor B. And then we have stuff coming in here. We got 1, 2, and then you go through a heat exchanger. Is it a counterflow heat exchanger? Let's see. Yeah, counterflow heat exchanger. I don't need to make it all because the diagram's above, but I'm going to just make enough of it so that we know what's going on here. So it comes in the big side and leaves the small side. Okay, so it's compressed. So this is CA and CB, and this is the heat exchanger. That's the international sign for heat exchange. This wiggly line. Okay, here we go. All right, now we got it. Okay, so what we're going to do is the reason why we're drawing these diagrams is we're going to take our control volume. So we're going to take a control volume here. Okay, we're going to take one here. And then there's going to be one here. So we're going to have 3 control volumes. We're going to have control volume 1, 2, and 3. Okay, so we're going to call this CV1. We'll call this CV2 and call this CV3. Okay, we got 3 different control volumes. Properties are given, right? Properties are given above, up here. I'm not going to rewrite them, but I'll just say props above. Okay, great. Now let's see. I think we're in good shape here. We got these different things. This is our diagram. We don't need to make any other kind of diagram. So let's go to the second page. Let's go example 1 continued. Zoom up. Oops, sorry. Zoom up here. Okay, so now the first thing we got to do is, I guess what we're going to do is we're going to find some states, right? So the first thing we're going to do is we're going to look for some states of the different gases. We can also write the continuity. We know that m dot 1 is equal to m dot 2 is equal to m dot 3 is equal to m dot 4. Because if we go back here, we can put some numbers on. Oops. We can say this is 1, 2, 3, 4. And I think did we say that's 5 and 6? Yeah, so this is 5 and 6. Okay, so if we do that, we know that all those m dots are, and we'll just call this m dot air, m dot a, okay, m dot a. Okay, so this is continuity. If we do the first law, let's say it's mass. First law. Let's see if I have my pen. Yeah, we're good. So the first law. Let's just draw the first law for control volume CV1. Okay, so we're doing the control volume only. We're doing the first law for only first control volume 1, right? Not the entire system. So 1 equals Q dot minus C A W dot C A plus m dot A, which is the mass flow of the air, times H1 minus H2. Let's just do it to be complete. Plus V1 squared minus V2 squared over 2 plus Z1 minus Z2. Bracket. These go away. We also said this was adiabatic, right? So then we have those things going away. All right, so then all we got to do then is simplify the problem to something pretty simple. So work CA, or the power CA, is equal to m dot A times H1 minus H2. Right, so when we're getting the compressor work for number 1. So now we have air, right? We need to use the tables. So use table, we'll use table A22 as I recall for air at the different temperatures. So we're given temperatures of, so H1, so let's go back here, let's find the temperature. So H1 is at 300 and 600. Remember, for an ideal gas, the enthalpy is only a function of what? Temperature. Right. Just want to make sure you had time to answer that. So, so at 300 degrees, we're going to find it, and then H2 at 600 degrees, right? Yes, at 600 degrees. So this is at 300, and this is at 600. Okay. All right, so now let's go back, and we won't do this for all of them, but we'll just go and see if we can find them, okay? So let's see here, if I can go to the book, and I could go here to the tables and SI units, since we're in SI units, thank goodness. We can go A22, which is the ideal gas properties of air, because we're dealing with air here. Notice that you have temperature and enthalpy right next to each other. Very convenient, okay? All good. Now let's see, we got H1 is, okay, so wait, A22, let's go back. Okay, here we go. So H1 is 300.19. I'm going to write that one down, 300.19 kilojoules per kilogram. And 600 is down here. So this, where's the 600? Oh, it's over here on the other side. 670 point right here. 670.4. Nope, that's not it. 607.02. So equals 607 point. Oops. I screwed up. Or I'll show you in a minute. 607.02 kilojoules per kilogram. That's all we need here, I think. That's all we need. So we'll go back. Okay, so we did that. Now we have to go here and we can just solve this thing because we have meters per second. I'm sorry, kilograms per second. So we have mass flow. So W dot CA is equal to 0.6, which is kilograms per second, the mass flow that we were given. Times H1 minus H2 is 300.19 minus 607.02. And this ends up equaling, just looking at my math that I have already done, negative 184 kilowatts. So that's answer to part of A1, if you will. Okay, so that's negative 184. Remember, it's a negative number, which means that there's work going into the control volume. Okay, so similarly, for compressor, so it's control volume, what did I call it? Control volume 2, sorry. Control volume 2. Okay, which we call it control volume number 2, right? Yeah. Okay. Control volume number 2, we had the similar deal. And so we're just going to say it is, we're going to repeat our first law. We're going to say that W dot CB is equal to M dot A times H3 minus H4. Is that right? H3 minus H4? Yes. And then if we're just going to obtain the same values from table A22, we're going to get the same values. So I'm going to leave that up to you guys to look those up. So this is 0.6 is the same mass flow because we didn't leak any air between those things, and the heat exchanger doesn't have any leaks in it. And then we're going to go here. So this is going to be 451.8 minus, what is it, 821. 821.95. So those are the enthalpies. And this is going to yield negative 222 kilowatts. I'll put a box around that. Okay, so and then we've done part A. So B. So now we can look at the heat exchanger. So now let's consider control volume 3, which is the heat exchanger. Okay, oops, if I can spell. Oh my gosh, that was horrible. Let's just get rid of this. Okay, heat exchanger. Okay, so I'm going to move me up here somewhere. Okay, so heat exchanger is here. Now we have to say M dot 5 equals M dot 6 equals M dot water. Okay, because that's pretty straightforward. And then we can say, M dot 3 and 4 are the air, so that's no problem. Or 2 and 3 are the air. We already written that. So for the heat exchanger on the water side and the air side, so essentially for the heat exchanger, we need to write the first law overall for the heat exchanger, right? So if we put the control volume all around it, we need to sum everything, right? So 0 equals Q, I'll just say heat exchanger plus work, oops, not plus, minus work heat exchanger, right? Plus the sum of the M dot coming in, N dot I, HI. We're neglecting kinetic and potential energy, okay? We're just going to do it. Minus the sum of M dot E, H, E. the enthalpies of stuff leaving. Okay, so now we have essentially taken into account all the enthalpies coming in and out of the heat exchanger, right? So now solving for this, so let's see. Example 1 continued. So solving for this from the first law for the heat exchanger, we get the following thing. We get 0 equals m dot 2, which is m dot air h2 plus m dot 5. M dot 5 is m dot 5 is m dot water h5 minus m dot a h3 minus m dot water h6. Okay, so those are all the sums of all those things. We make sure to balance the whole energy for the whole thing. Now it's adiabatic, so that the heat term goes away. Did I actually cross that out? No, of course not. So there's no heat and work, right? So these go to 0. Sorry. Someone would ask me that one. Okay, so those goes to 0, so then we're just left with this for the heat exchanger, okay? Now, now let's see. Now, all we have to do is just kind of incorporating this thing. We can put it all together, so let me get the eraser on here. Okay, so let's see. Rearrange. So I rearrange the equations. We're going to get m dot water, because that's what we're trying to find, remember, equals m dot air times h2 minus h3, which we know because we looked those up already, h6 minus h5. Now, the only thing we don't have are the h5 and h6. So h5 is equals to hf of water at, oh boy, we have to go back a couple pages for this. That looks like h5 is at 20 degrees C. 20, and h6 is equals hf at 30 degrees C. Okay, so let's go here and go back to the tables. So now we go back to table, let's see, oops, gotta go to tables. Okay, tables, I'm looking for saturated water temperature table. And so 30 degrees C is here, so HF is 125.79. I'm gonna write that down. 125.79. Oops. Kilojoules per kilogram, and H6 is at 30 degrees C, which is down here. HF is, which is, oops, no, that was HF. 20 is, oh shoot. I'm sorry. So what is it? H6 is at 30 degrees C, and that's 125.79. 125.79. What? You guys are kilojoules per kilogram. Hopefully not completely confused. No, just erase this one. So H5 is at 20, so that's 83.96. Okay, let's go do that. 83.96. Okay. All right, good. So then we got those that we need, and then all we got to do is put those into our equation and get the answer. So m dot of water is equal to 0.6, which is the mass flow of air, 607. These are numbers we found before. 02 minus 451.8 all over 125.79 minus 83.96, right? And then we just solve that in our calculator, and we get 2.23 kilograms per second. Okay, 2.23 kilograms per second is the answer. Okay, so you can see what we did. We took individual control volumes to solve for each of the little individual processes to find what we're looking for. Now, if we wanted to, we could have, look at this problem again here. Let's go back to this problem. We could, if I wanted to say, well, what's the overall, if I was to ask you for what, the condition of T6 was, and I had these things and I had the work, you could probably figure it out, right? If you took a control volume around the entire thing. So sometimes you just need to be able to choose the control volume that you need to solve the problem. So this gets tricky. It's something that I would practice, and maybe hopefully I can get you a homework problem that makes you think a little bit about the control volume that you take. Okay, so let's see, where am I at? Oh, 30 minutes. Okay, so now let's go to the next one. So this is one. I thought I'd go to maybe a little bit more relevant problem that we can talk about. And this one is about pumped hydro. Okay, so I'm going to talk a little bit about pumped hydro. So let me get out of here. Okay, so the figure is showing a pumped hydro energy storage system delivering water at steady state from a lower reservoir to an upper reservoir using off-peak electricity. All right, so electricity is used, in this case, to run a pump, which then pumps water from this lower reservoir up to the upper reservoir. Okay, delivered to the upper reservoir at a volumetric flow rate of 150. Now, we haven't done volumetric flow rate yet, but it's easy, okay? It's a matter of just doing some density calculations, and then you can get mass. Okay, so then there's an increase in elevation at 20 meters, which really isn't very high, actually. There's no significant change in temperature, pressure, kinetic energy from inlet to the exit, so we can assume that there's nothing of that. Heat transfer from the pump to its surroundings occurs at a rate of 0.6 megawatts, and G equals, so gravitational energy is 9.8 meters per second squared. Okay, determine the pump power required in megawatts. Assume that the same volumetric flow rate when the system is generating on-peak electricity using this water. Will the power be greater or less than the same as the pump power? Interesting. This is an interesting question. Now, pumped hydro, you might ask, what is this all about? You don't really know what that is. Let me just show you. I have a slide that I will put in the note in the slides. I haven't updated this one, but essentially, there's a good video, a really good video that I found on YouTube, and that video is found here. I'm not going to show it to you here because you can always just click it and go find it, but I recommend watching it. It's really interesting. It's about practical engineering, and it talks a little bit about pumped hydro. So I think it'd be kind of an interesting thing for you to watch. So feel free to do that if you have time. So essentially, the idea behind pumped hydro storage is that in times of low electrical power demand on the grid, excess generation capacity is used to pump water into an upper reservoir, using the gravitational potential energy of that later converted to work through the same turbine, generating electricity. Now, you might ask, why the heck would we want to do this? Well, the idea is that some types of renewable energy, like wind and solar, for example, are generated at times when the grid doesn't need the energy, right? Sometimes they call this stranded capacity. And these things go idle because they can't use the electricity. So what you want to do is you want to save the electricity somewhere, save it in some sort of storage system. Now, batteries you could use, but batteries are rather expensive, especially for the kind of power that we're talking about in the megawatt range. Batteries are going to be very expensive. So one really kind of useful thing you can do is if you've got water in a reservoir that's high up and you have a lower sink, the lower reservoir like an ocean or something. In this case, it has this, you can see here in my picture, has got a sea, and then there's a generator and a pump turbine generator. And then, you can pump up to the reservoir, and then when you need the energy, you can do that. So for instance, here's an example of I'll go in here. So the pump power, so during the time of day that you need it, so at night, say for example, if you're running a wind, because wind often actually generates a lot at night, because it can be windy at night in some places of the country or the world, and you want to use that. But unfortunately, everybody's sleeping, so you can't use it. So what happens is you use the pump power and you pump up the water into the reservoir during the night, and then during the day, you use it as you want, right? And the nice thing is that this is very throttleable. You can change the amount of power that you get from these systems very easily by just kind of changing the valve or putting some sort of regulator here to regulate how much power you can get out of these systems. So it's really convenient, right? So and it's a really good way to store renewable energy that you make at off-peak times. Okay, all right. So as I said, watch this video. It's pretty cool. And we can go on with we haven't gone back to the example problem. One thing I was going to note is that energy recovery of 70 to 80% can be achieved, and that's what we're going to kind of talk about: is how much power can you get out of this thing versus how much power do you have to put in, right? And what we're going to learn in the second law is you can never get the same amount of power out that you put in, so it's always going to be some kind of loss, and we're gonna try to get to that, to the bottom of that, today. Okay, so now let's do this example problem before I run out of time. Okay, so here's the example problem. So the figure shows a pumped, here, let's see, tablet's logging me off again, so let's go here. Let's go to my example problem. So now we have a pumped hydro energy storage system delivering water at a steady state from a reservoir. And I already read this, so I'm not going to go through it again. All right, so let's just go through what we have to find. So we'll say known. Restate essentially what we need to do the problem. So if we have a steady state, so we have a steady state pumped hydro system. Okay, a steady state pumped hydro system. We have the pump power required in megawatts. Find, say, W dot of the pump in megawatts, and we also needed some kind of discussion about whether the power would be greater when the system generates on-peak electricity. So when we actually want to generate the power, will we have the same power output now that we had to put in? And I think you're probably thinking no, but okay, let's do the analysis. So let's see, assumptions. So let's do a couple assumptions here. So the first assumption is that the, so one, we are at steady state. All right, so we're actually, I just want to make sure. So we're delivered, yeah, so we're pumping water up to the reservoir. So we're going this way, right? Okay, so pumping up that way. Assumption steady state. Two, I think we have some heat loss, right? So we can't assume adiabatic. There's no change in temperature pressure. So we're going to assume there's no delta T happening. There's no, for the pump, so we have to assume something about the pump here, right? So essentially for the pump, we have to assume that the no change, what did we say? No change in temperature, pressure, kinetic energy from inlet to the outlet. So there's no change in delta KE or delta PE, from the pump. Delta PE for the pump itself. Let's see. Delivered to the upper reservoir, there's no significant change in temperature, pressure, kinetic energy from inlet, so to the outlet. Okay, so, and no change in, no delta pressure from inlet to the outlet. Okay, so we have, that means at the top and the bottom of the reservoir. So, so we assume gravity at 9.81 meters per second squared, which is nowhere on Earth, so that's good. We're going to want incompressible water, and I don't think we need to do anything with temperatures here, because we are assuming that essentially the temperature is not changing, right? It's going to be same temperature inlet and outlet, so we don't have to really worry about it. But I guess we're just going to assume that density is 1,000 meters. Density is kilograms per meter cubed, or 0.001 meters cubed per kilogram for V dot, right? Or for little v. Okay, and all right, so that's good. So if we look at what our control volume is going to be, essentially what we're going to do is we're going to take the well, no. Did I say anything about? Hold on here. Hold on. I'm a little confused. Oh no, we have to have potential energy. Why did I do that? Okay, so no pressure, but the potential energy. If I was in class, you guys would definitely be on me about this one. Okay, there's definitely potential energy because, because that's what we're trying to reclaim here. Oh boy. So let's just let's see if I can just take this guy and move it over here. No, I'm just going to erase it. I'm going to try to just draw here, so delta pressure. Okay, good. I'm still getting used to this tool here. All right, so now let's see. We're going to take the overall system here. If I just take what the overall system is, diagram. Okay, so here I've got water. I'm just going to draw it like this, and you have a pump. This is the engineering diagram for pump. It's like a circle with a triangle in it, okay? And then you have a, so circle, and then you have another reservoir down here at some other level. So this is the delta G, delta Z rather. So some change in elevation. Your control volume, if I just make this really basic, right? So my control volume, I'm just taking it to be the overall system here. Okay, and then there's some work going in here. Actually, usually draw work coming out, right? It's going to be negative work. So there's worked out of the pump. Okay, so there it is. That's our control volume. So this is the upper reservoir, and this is the lower. Okay, so now let's solve this thing. So now let's write the first law for pumping water up. Okay, so the first law for pumping water up looks like this. So let's just write out the first law. 0 equals Q dot of the pump minus W dot for the pump plus M dot, which is the flow rate, H1 minus H2 plus V1 squared minus V2 squared over 2 plus G Z1 minus Z2 squared. Not squared, sorry. Z1 minus Z2. Okay? And then so essentially the only thing we've got is, so we said neglected this guy. We neglected this guy because there's no temperature change, no delta T. We definitely have work for the pump, but we don't have heat. Oh wait, did we have heat? We did, didn't we? Wait a second. Go up, go up. Yes. We have some heat. So we can't assume that this is 0. Okay. All right, so now let's just continue on. So let's see. So now we have this pretty simple equation. So work of the pump is equal to Q of the pump. Or is this heat loss from the overall system? Heat transfer from the pump to its surroundings. Okay, no. Okay. Q of the pump plus M dot G Z1 minus Z2. Okay, so then we have everything, right? So we have 0.6 megawatts. Now this is heat loss, so 0.6 megawatts is what we're losing, right? Oh no, it's 0.5 megawatts according to the problem. So let's go back here. No, 0.6 megawatts to the surrounding. Yeah, so 0.6 plus. Now this is 1,000. So this is going to be an M dot here. So this is 1,000 kilograms per meter cubed times 150. Here, let's do the units here. So 1,000 kilograms per meter cubed times 150 meters cubed per, is that meters cubed per second, right? Times 9.81 times Z1 minus Z2, which is minus 20 meters, because we're going back up. So Z1 minus Z2 is minus 20. And then we should get, let's see, now we're going to think about it here. We're going to get this thing in watts. So this is in megawatts, right? And this is going to be in watts because we got kilograms meter cubed. So this is going to be in watts. So we're going to actually have to take this guy and divide this one by 10 to the 6 watts per megawatt. Okay? So this is example 2 continued. Okay, how am I doing time-wise here? Oh, I'm almost done. Okay, I'm almost done now. That's good. I'm almost finished. So then this is essentially the power required is something like equals so work of the pump. If we just solve this thing and put it in our calculators, we have negative 30 megawatts. Okay, that's a lot of power. That's a lot of power. That's the power required. Required power to pump water is 30 megawatts. All right, that's a lot of power, and that's have to come from your solar farm or whatever it is going to be. Now, there's going to be all sorts of things that you need to do. There's going to be losses and other things like that. So you would say that probably if you're going to go to the question here is assuming the same volumetric. So if I go back up to the problem, it says assuming the same volumetric flow rate when the system generates on-peak electricity using this water, will the power be greater, less, or the same? So if we're going to go the opposite direction, the power rate is developed will be probably less than 30 watts because 30 megawatts. We're going to say because essentially because essentially we required a certain amount of work to get this thing up, a high amount of work. When it comes down, we're not going to get the same amount of work. Well, there's going to be some losses. We're going to say, because I'm dancing around this because we're going to be doing second law analysis pretty soon, and that's when we're going to talk a little bit about what the different kind of loss mechanisms there are and how we account for that. But then we're going to just say there are probably losses in the pump and turbine such that the work dot of the turbine out during generation of electricity will be less than 30 megawatts. Okay? There's got to be some losses. You can never get everything back what you put in. Okay? There's no such thing as a free lunch, and you can't even get that good. Okay? And we're gonna learn much more about that when we get into the second law. Probably on Friday even we're going to start talking about irreversible systems and reversible systems. So stay tuned for that. All right, so I think that's it for me for today. The next lecture will be for Wednesday. Make sure you go and do the survey for Monday. When you get on and you see my lecture, go back and I'll have probably a couple survey questions for you to do that have to do with this lecture. So please go ahead and do those, and I look forward to seeing you again on Wednesday.